A colossal ring in space could one day carry entire cities around our planet. This is the stunning reality proposed by the concept of orbital rings, a megastructure that would fundamentally reshape where and how humanity lives. By the end of this exploration, you will understand the science that makes this possible and the future it could unlock. How could a structure that large remain stable without crashing down? And what would daily life be like in a home that glides across the sky? Does the idea of a mobile civilization orbiting Earth spark a sense of wonder or concern for you? This radical vision did not appear from nowhere. It was born from the minds of thinkers who looked at the heavens and saw not just stars, but blueprints. Long before the technology existed to attempt such a feat, pioneers like Konstantin Tsiolkovsky and later Birch were performing the mental gymnastics required to conceive of a ring around our world. Their work was not merely engineering, it was a profound philosophical shift, a declaration that humanity's home need not be a static piece of ground. They calculated the immense forces, theorized about the materials, and grappled with the fundamental question of how to keep such a structure aloft without it collapsing under its own weight or plummeting to Earth. This was the essential first step, moving the concept of a city from a fixed location to a coordinate in motion, a place defined by its journey rather than its geography. To understand how they solved the puzzle of stability, we must look to a force so common we rarely give it a second thought. That outward push is the simple, brilliant secret to keeping the ring in the sky. Think of it like a hula hoop spinning around a person's waist. The hoop itself isn't magically glued to the person. It's the constant, rapid spin that creates a force pushing outward, preventing the hoop from simply falling to the ground. Now scale that idea up to a planetary level. An orbital ring operates on the same fundamental principle, but instead of a child's toy, it is a stream of matter or a solid structure moving at incredible speeds around the Earth. This motion generates a powerful centrifugal force, a relentless push away from the planet's center. This outward push is locked in a perfect, perpetual tug of war with Earth's gravity, which is constantly pulling the ring inward. When these two immense forces are perfectly balanced, the ring achieves a state of graceful equilibrium, holding its position in the void. This is not a stationary platform. It is a structure in constant high-speed motion, and that very motion is the source of its stability. Without that relentless forward rush, the entire assembly would succumb to gravity's pull. But with it, the ring becomes a stable, unmoving foundation from our perspective on the ground, a fixed track in the sky upon which the future can be built. This elegant balance, however, creates its own monumental challenge. What kind of material could possibly withstand the titanic forces straining to pull such a ring apart from the inside? The very forces that grant the ring its stability also threaten to tear it apart from within. This is the great paradox of the orbital ring, a challenge that demands a completely new class of material. We are no longer talking about steel or titanium. We are talking about carbon nanotubes and graphene, substances with strengths measured on an almost mythical scale. Imagine a cable thinner than a human hair yet stronger than a diamond thread, woven across thousands of kilometers. These are the hypothetical materials that could shoulder the immense tensile strain, the constant pull trying to rip the structure to pieces. But even these supermaterials might not be enough on their own. This is where the concept of active support transforms the entire endeavor. Think of it not as a static bridge, but as a living, breathing entity. A network of sensors and actuators would run through the ring's entire length, constantly monitoring stress and making microscopic adjustments in real time. It is a dynamic dance of compensation, a system that actively fights back against the forces of gravity and momentum to maintain its perfect fragile balance. The scale of this engineering is almost beyond human comprehension. It dwarfs every skyscraper, every dam, every bridge we have ever built combined. To even contemplate such a project requires a fundamental shift in our thinking, from constructing objects to orchestrating forces on a planetary scale. How would we possibly assemble something so vast in the void of space, and what would be the first practical step toward turning this cosmic blueprint into a reality? Assembling such a colossal structure presents a logistical challenge unlike any humanity has ever faced. The sheer quantity of material required is staggering, far too vast to launch economically from Earth's surface. This forces a radical rethinking of our entire supply chain. Instead of looking down at our planet, we would look outward to the moon and the asteroids, turning the resources of our celestial neighborhood into the literal building blocks of our future. Automated robotic miners would harvest raw materials, while orbital factories, operating in the quiet efficiency of microgravity, would use advanced three-dimensional printing to transform that raw ore into finished components. Picture massive orbital shipyards, silent and sprawling, where robotic arms guided by sophisticated artificial intelligence assemble these pieces into ever larger segments of the ring itself. This would not be a single, monumental launch, but a slow and deliberate crescendo of construction. It would likely begin with a small, non-rotating cable, a fragile thread placed carefully in a stable orbit. This initial strand would serve as a construction backbone, a foundation to which more material is gradually added year after year, decade after decade. The process would be incremental, a patient accretion of mass and complexity until the structure is robust enough to be set into its final, majestic spin. This phase of the project would span generations, a testament to long-term thinking that transcends individual lifetimes and national borders. It would demand unprecedented global cooperation and a level of sustained funding that rivals the gross domestic product of entire nations. This immense cost forces a critical question, one that goes beyond pure engineering. What powerful economic incentive could possibly justify such a monumental investment, and what would it take to build not just the ring, but the political and economic will to see it through? The staggering cost of an orbital ring finds its justification not in a single breakthrough, but in a symphony of economic revolutions working in concert. Lift the first payload from Earth to the completed ring, and you witness the birth of the most efficient spaceport ever conceived. Instead of a violent, fuel-guzzling rocket launch, cargo and passengers ascend smoothly along a space elevator, a tether dropping down from the ring's stable height. This transforms access to space from a monumental, expensive effort into a routine railway journey, slashing the cost of delivering materials into orbit by orders of magnitude. With the highway to space now open, the ring itself becomes the ultimate industrial park. Envision vast, silent factories housed within its structure, harnessing the pure vacuum and zero gravity to manufacture products impossible to create on Earth, from flawless crystal spheres for electronics to revolutionary new metal alloys. Above these factories, immense arrays of solar panels, unhindered by clouds or atmosphere, capture sunlight with relentless efficiency, beaming clean power down to a waiting world. The ring then becomes a bustling port for interplanetary commerce, a gravitational stepping stone where spacecraft can be assembled and launched to the Moon, Mars, and the asteroid belts with a fraction of the fuel required from Earth's deep gravity well. Each of these ventures alone could redefine global economies. Together, They form an interconnected economic engine so powerful that the initial investment, while vast, begins to look like the foundational cost of opening the entire solar system to humanity. This financial logic ultimately transforms the ring from a megastructure into a metropolis, a place not just for industry but for life itself. What would it be like to call a city that orbits the planet your home? These orbiting cities would feel more like a familiar neighborhood than a cold machine. Picture wide, open plazas bathed in simulated sunlight, where the air smells of freshly cut grass from a nearby park, not recycled oxygen. Gentle streams could meander through public squares, their water endlessly purified and reused by silent, sophisticated systems that make waste a forgotten concept. Above it all, vast projected skies might shift from a brilliant blue day to a star-dusted evening, creating a comforting rhythm for a community disconnected from the planetary cycle. The ground beneath your feet would feel solid and normal, thanks to large rotating sections of the city. This spin creates a force that mimics gravity, gently pressing you downward so you can walk, run, and live without the floating uncertainty of a space station. Life here is defined by perpetual, graceful motion. Your window would frame a living mural of our planet, a breathtaking panorama that slowly scrolls by, revealing emerald forests, sapphire oceans, and the swirling white tapestry of weather systems. One moment you are looking down at the vast, sandy expanse of the Sahara, and a few hours later, the lush green canopy of the Amazon fills your view. This constant panoramic journey would fundamentally reshape our sense of place. The very idea of a hometown transforms from a fixed point on a map to a path traced around the world, a continuous voyage shared by an entire community. How would this unprecedented perspective, this daily reminder of Earth's unity and fragility, change our culture, our politics, and our very identity as a species? This constant motion would demand a complete reinvention of our most fundamental social structures. How do you govern a city that, from a legal standpoint, is perpetually in transit over international waters and the territories of Earth's nations below? The very idea of a border becomes fluid, a line on a map that your home crosses every 90 minutes without ever touching. This could give rise to the first truly post-territorial states, political entities defined not by the land they control, but by the shared infrastructure and community of the ring itself. Their laws would likely be a unique hybrid, a new legal framework forged in space to handle everything from commerce to conflict, separate from the planetary jurisdictions scrolling by beneath them. Citizenship would transform from a birthright tied to soil to a conscious affiliation with a moving civilization. The culture flourishing in this environment would be inherently global, a tapestry woven from every tradition on Earth, yet distinct in its universal perspective. Daily life immersed in the panoramic view of a borderless planet would naturally foster a sense of shared human destiny, a collective identity that transcends old divisions. Yet this very advancement could create a new, profound rift. The ring dwellers, with their advanced technology and cosmic vantage point, might be seen as an elite class, potentially creating a societal stratification between the orbital and the terrestrial. This is the great social challenge of the ring, a test of whether humanity can build a new home in the sky without casting a shadow on the world below. The ultimate purpose of this mobile foundation, however, reaches far beyond these initial settlements, pointing toward a future where the entire solar system becomes our backyard. These cities would glide along their orbital track as smoothly as a train on a magnetic rail, their motion a silent and constant ballet. The secret lies not in engines attached to the cities themselves, but in the interaction between the city's foundation and the ring's relentless spin. Each urban center is a colossal module locked onto the ring by a system of magnetic levitation. This creates a near-frictionless cushion of force, a tiny gap of nothingness that separates the moving city from the rushing structure below it. To change a city's position, you would not fire thrusters but simply adjust the magnetic fields. By subtly increasing or decreasing the speed of the city relative to the ring's own velocity, you command its journey. A slight reduction in relative speed, and the city begins to drift backward along the ring's circumference. An increase, and it glides forward. To park a city, you synchronize its speed perfectly with the ring's rotation, holding it in a fixed position relative to the ground far below. This control unlocks profound possibilities. A city could perpetually chase the dawn, its streets always bathed in morning light while its night is brief and artificial. It could steer a wide berth around a churning hurricane, its path a graceful arc avoiding the storm, or it could reposition itself to align with a major spaceport tether, optimizing the flow of goods and people from Earth. This elegant system, however, is not without its perils. A significant failure in the magnetic guidance or power supply could, in a worst-case scenario, cause a city to lose its precise synchronization. The result would not be a sudden crash, but a gradual, uncontrolled drift, a loss of its intended orbital path that would require immediate and complex correction to prevent a long-term crisis. The smooth, silent motion of these cities represents a pinnacle of control, but it is a control that must be vigilantly maintained against the unforgiving physics of space. The integrity of the ring is a battle fought on an unimaginable scale, a silent war against physics itself. Every single component endures a relentless assault of forces. Beyond the steady pull of gravity and the immense outward push of its own spin, the structure must absorb the constant, shifting weight of entire moving cities. Each time a metropolis glides along its track, it sends vibrations and stresses rippling through the entire framework. Then there are the external threats, like microscopic particles of space debris striking at velocities faster than a bullet, slowly eroding the outer hull over centuries. Even the sun itself is a challenge, as one side of the ring bakes in direct sunlight while the other side faces the deep freeze of space, causing continuous expansion and contraction. To manage this, the ring would need a nervous system, a planet-spanning network of millions of sensors embedded within its structure. These sensors would constantly monitor for the slightest strain, the tiniest crack, or a dangerous temperature gradient. This data would feed into a central artificial intelligence, which could then dispatch swarms of automated repair bots to any trouble spot. These robotic workers, no larger than your hand, would scurry across the exterior and interior, performing microscopic welds, applying self-healing sealants, and replacing damaged panels. Redundancy is the golden rule here. Critical systems would have backups for their backups, and power would be distributed through multiple, independent grids. A single point of failure is not an option because a major structural breach would not mean a sudden, dramatic collapse. Instead, it would trigger a cascading failure, a wave of imbalance that could unravel the ring's careful equilibrium across thousands of kilometers. This relentless, automated vigilance is the price of safety for the millions living aboard. Yet, even this intricate physical defense system has a profound weakness, one that comes not from impacts or strain, but from an invisible source far more powerful than any hurricane. Beyond the immense physical forces, the ring's environment presents a silent, invisible danger. Our planet protects us with a thick blanket of air and a powerful magnetic shield, deflecting the sun's harsh radiation and burning up most space dust before it can reach the ground. An orbital ring has no such natural protection. It floats in the void, fully exposed to the full fury of the sun and the relentless peppering of micrometeoroids. particles no larger than a grain of sand but traveling faster than a high-powered rifle bullet. To make these cities truly livable, their habitats must be encased in a formidable armor. The walls themselves could be layered with meters of material, perhaps using lunar regolith or water stored in vast internal tanks, both of which are excellent at absorbing harmful radiation. Wrapping the entire structure could be an artificial magnetic field, a technological echo of Earth's own, designed to gently push charged particles away from the inhabited sections. The outer hull would be a multi-layered shield, a sacrificial skin designed to vaporize incoming particles upon impact, dissipating their immense energy across a wide area to prevent a breach. This is not a one-time construction task but a continuous, automated defense. A global network of telescopes and sensors would constantly scan the surrounding space, tracking debris and providing early warning, allowing the cities to make minor adjustments if a larger object is predicted to cross their path. This intricate, multi-layered protection system is absolutely fundamental, a non-negotiable requirement for any permanent human presence. It ensures that the vibrant life inside the city continues undisturbed by the hostile conditions outside. This very necessity for absolute protection, however, raises a profound and difficult question about our future in space. How would such a vast and critical structure be safeguarded in a world where conflict, unfortunately, still exists? The measures needed to ensure its security could reshape our very understanding of safety and sovereignty. This constant, open exposure presents a security challenge unlike any a city on Earth has ever faced. There are no natural barriers, no hidden valleys in which to conceal vital infrastructure. Every kilometer of the ring is visible, a stark silhouette against the bright backdrop of our planet. This vulnerability forces a complete rethinking of protection, moving beyond walls and gates toward a system of integrated, layered awareness. The first line of defense would be a pervasive and intelligent sensor network, a planetary-scale immune system constantly scanning for anomalous behavior, from an unauthorized approach by a small craft to a subtle, internal pressure change that might indicate tampering. This surveillance would be paired with non-lethal point defense systems, perhaps using targeted energy or precise projectiles to safely disable a threat before it could reach the structure, much like a body's white blood cells neutralizing a pathogen. Yet technology alone is insufficient. The ultimate safeguard would be a foundational political agreement, an international treaty established long before the first segment is assembled, designating the entire ring as a permanent neutral zone, a demilitarized sanctuary for all humanity. Its governance would need to be a transparent consortium of nations, ensuring that no single Earth-bound power could claim it, making an attack on the ring an attack on the collective interests of the entire species. The very act of building it would therefore require us to achieve a new level of global cooperation, making the structure not just a symbol of technological prowess, but a testament to our political maturity. This intricate web of sensors, defenses, and treaties all demands a colossal and uninterrupted flow of power to remain vigilant. The energy required to protect the ring is only a fraction of what it needs to simply exist. This constant demand for power makes the ring's energy system its beating heart, a circulatory network of immense scale. Vast fields of solar panels would stretch along its sunward face, their surfaces drinking in the raw, unfiltered energy of the sun 24 hours a day. Without an atmosphere to diffuse the light, their efficiency would dwarf anything possible on Earth. Yet solar power alone may not be enough to meet the staggering demands of propulsion, life support, and the constant, energy-intensive corrections of the active support system. For the darker stretches of its orbit or for sudden power surges, the ring would need deep reserves. One elegant solution involves beaming supplemental energy from the planet below. Giant ground-based facilities could target precise microwave or laser beams toward receiving antennas on the ring's underside, transferring power across the void without a single physical connection. Looking further into the future, if the technology matures, compact nuclear fusion reactors could be embedded within the ring's structure, offering a dense, nearly limitless power source that would make the entire system truly energy independent. The sheer scale of this energy budget is planetary, requiring breakthroughs not just in generation, but in storage and transmission. Superconducting cables, chilled to near absolute zero by the cold of space, would run the entire circumference of the ring, distributing power with almost no loss across tens of thousands of kilometers. This is not merely about keeping the lights on in the cities. It is about maintaining the delicate balance of forces that keeps the entire structure from tearing itself apart. The sheer abundance of power generated, however, creates a profound opportunity. The ring could become a utility for the world below, beaming gigawatts of clean solar energy down to receiving stations on Earth. This single function could fundamentally address our global energy crisis, replacing fossil fuels and ending our reliance on carbon-intensive power generation. The environmental impact of such a shift would be transformative, turning a megastructure of consumption into a guardian of the very planet it orbits. The ultimate environmental impact of an orbital ring is a story of two timelines. In the short term, the price of admission is steep. Launching the initial construction infrastructure would require a massive surge in rocket activity, temporarily increasing emissions in the upper atmosphere. The resource extraction needed is equally colossal, likely shifting from terrestrial mines to automated operations on the Moon and asteroids. While this spares Earth's own landscapes from further scarring, it represents humanity's first large-scale industrial imprint on the celestial realm, a permanent expansion of our resource footprint beyond our home world. This initial environmental cost, however, must be weighed against a long-term vision of profound planetary healing. Once operational, the ring offers a clear path to offloading our most polluting industries. Imagine the smelters, the chemical plants, the high-tech manufacturing facilities that currently dot our landscapes, all relocated to the controlled, closed-loop environment of the ring. Earth would no longer be the factory floor, but could begin a slow and deliberate recovery. The ring's most direct contribution could be a constant, clean energy supply. Vast solar arrays, unhindered by night or weather, could beam gigawatts of power to the surface, making fossil fuels a relic of the past and drastically reducing the carbon blanket enveloping our planet. This structure would also serve as the ultimate observation deck, hosting sensors that monitor deforestation, track ocean health, and provide unprecedented early warning for natural disasters, giving us the tools to become better stewards of our world. This dual role as both a potential initial stressor and a long-term guardian forces a difficult calculation. Is the temporary disturbance worth the chance for Earth to truly breathe again? And what new responsibilities do we take on when our solutions become so large they cast literal shadows? The placement of such a massive structure is not without its subtle physical effects on the planet. A completed orbital ring would be wide enough to cast a faint, moving shadow on the Earth's surface during certain times of the day. This would not be a sudden, dramatic eclipse, but a gentle, fleeting dimness, a soft gray line tracing a path across the oceans and continents. For the ecosystems below, this would be a new and regular feature of their daily light cycle. Scientists would need to carefully model the potential impact on agriculture, phytoplankton in the oceans, and local weather patterns that rely on direct sunlight. The structure's presence could also influence the very highest layers of our atmosphere and the density of the Van Allen radiation belts, creating a new, human-made element in our planet's intricate orbital mechanics. Furthermore, the process of construction and the ring's ongoing operation would inevitably add to the growing cloud of space debris, requiring a rigorous and constant regimen of tracking and cleanup to prevent a cascade of collisions that could threaten the ring itself and all other satellites. This highlights a fundamental truth of such grand projects. They do not simply exist in space, they become a permanent part of our planet's extended environment, a new layer of complexity we are responsible for managing in perpetuity. The ultimate justification for this careful stewardship may lie not just in protecting Earth, but in how this technology could be applied to other worlds, transforming dead rocks into new frontiers for life. The principles that could one day encircle our world are not confined to Earth alone. This same technology could be adapted to transform our entire solar system, turning hostile planets into stepping stones for civilization. A ring around Mars would face the challenge of the planet's weaker gravity, which would require a different balance of forces to maintain stability. Yet this structure could become the central nervous system for a global terraforming project. It could support giant, adjustable solar shades positioned at strategic points, carefully managing the amount of sunlight reaching the surface to warm the planet and melt the polar ice caps. The ring itself would serve as the primary spaceport and transport hub, connecting fledgling colonies and coordinating the delivery of materials across the vast Martian landscape. Venus presents an entirely different puzzle. Its surface is a hellish furnace, but high in its upper atmosphere, the temperature and pressure are surprisingly Earth-like. An orbital ring here might not be a solid structure in the traditional sense. It could be a floating ring, a dynamic system of pressurized habitats and platforms suspended in that temperate layer, offering humanity its first permanent foothold in the Venusian skies. Around the gas giants like Jupiter, the challenges escalate dramatically. The planet's immense gravity and ferocious radiation belts would require rings built with even more robust materials and formidable shielding. But the reward would be access to a cosmic treasure trove. These rings could serve as stable bases for operations mining the deep atmospheres for rare isotopes like helium-3, a potential fuel for the clean fusion reactors of the distant future. Each planetary environment demands a bespoke engineering solution, proving the orbital ring is not a single design but a versatile template. This universality suggests it could become the fundamental infrastructure for a truly multi-planet species, a network of celestial highways connecting our future among the stars. That very ambition pushes the concept to its absolute limit, toward structures so vast they defy conventional understanding. This hybrid design masterfully separates the problem of stability from the need for gravity. The colossal ring itself remains static, a fixed celestial highway locked in its perfect balance with the planet's pull. But attached to this unmoving backbone are the cities, and these are not static blocks. They are vast, rotating cylinders, each one a self-contained world spinning on its own axis. As these cylinders turn, the centrifugal force pushes everything inside outward toward the interior walls. This force acts exactly like gravity, providing a firm, familiar downward pull for everyone living within. You could walk through a park, feel the weight of a book in your hand, or pour a glass of water, all with the same natural sensations you experience on Earth. This solves one of the most significant health challenges of long-term life in space, preventing the bone density loss and muscle atrophy that occur in prolonged weightlessness. The engineering that makes this possible is as elegant as it is complex. The point where the spinning city connects to the stationary ring is a marvel of precision. Imagine a colossal, frictionless bearing, a circular interface where the rotating habitat meets the non-rotating foundation. Through this narrow, technologically profound junction, all the necessities of life must flow. Power cables, data lines, water pipes, and transportation tubes all require intricate magnetic couplers that can transfer resources across a boundary of motion without a single physical wire ever twisting or breaking. Transferring from the ring into a city would be a unique experience. You would enter a docking port on the non-rotating ring, step into a compartment that slowly begins to match the city's spin, and only then walk through an airlock into the bustling, gravity-filled interior. This intricate dance between the moving and the still pushes our mechanical ingenuity to its absolute limit, serving as a crucial test for the even more ambitious structures that may one day define our future among the stars. This connection between orbital rings and free-floating habitats is not a new idea, but a powerful revival of a grand vision. Decades ago, physicist Gerard K. O'Neill looked beyond the Moon and Mars, proposing that humanity's future was not on planetary surfaces, but inside vast, self-sufficient cylinders floating in the emptiness of space. An orbital ring can be seen as the logical evolution of his O'Neill cylinder, a linear version of that same rotating habitat. Or, on an even grander scale, the ring becomes a celestial highway, a fixed transportation spine connecting dozens of these independent cylinder worlds. This synergy creates a scalable model for space colonization that is both practical and profound. The ring provides the essential infrastructure, the stable backbone for power distribution, commerce, and transport. The cylinders, in turn, provide the living space, the familiar, Earth-like environments where communities can grow and thrive, each with its own unique culture and character. This represents a fundamental philosophical shift, a move away from planets as our primary homes and toward habitats that we design and build ourselves. It redefines our place in the universe from tenants of a world to architects of our own destiny. This expansive vision forces us to confront the ultimate purpose of such endeavors. Are we building these megastructures to escape a troubled Earth, or are we fulfilling a deeper, more ancient imperative to spread life and consciousness beyond its cradle? The answer to that question may determine the kind of civilization we become among the stars. The ultimate expression of this technology transforms the ring from a home into a propulsion system for an entire world. Imagine a network of rings so advanced and powerful that their collective thrust could ever so slowly adjust the orbit of our planet itself. This stellar engine would use the ring's own momentum or channel vast amounts of solar energy, creating a gentle but continuous push over millions of years. Such a capability could one day become a necessity, a way to carefully steer Earth away from a future existential threat or to optimize our position within the evolving solar system. This is engineering on a truly geological timescale, a project for a civilization thinking not in centuries but in eons. Alternatively, the ring could be cast in a different, equally epic role. It could be deliberately detached from its planetary anchor and set on a course for another star. In this configuration, it becomes an interstellar ark, a self-contained world embarking on a voyage that would span thousands of generations. Within its rotating habitats, an entire ecosystem and human society would be preserved, carrying the collective knowledge and culture of humanity to a new stellar neighborhood. These visions exist at the very frontier of what is physically possible, requiring mastery over forces and energies we can barely comprehend today. They are less blueprints and more philosophical provocations, challenging us to consider the ultimate purpose of our expansion. Are we building to secure our future on this one planet, or are we laying the groundwork for a civilization that will one day learn to move worlds and sail the sea of stars? This expansive view of the far future inevitably grounds us in the tangible challenges of the present moment. The materials needed to build an orbital ring do not yet exist in any meaningful quantity. Our strongest steels and alloys are like soft clay compared to the diamond-like resilience required. The primary challenge is tensile strength, the ability of a material to withstand being pulled apart. To endure the titanic forces within the ring, we would need fibers with strengths measured in terapascals, a unit of force that is thousands of times greater than what high-grade titanium can manage. This points toward a class of materials that currently belong more to laboratories than to construction sites: carbon nanotubes and diamond nanothreads. These are not bulk materials you can forge in a furnace. A carbon nanotube is a sheet of carbon atoms rolled into a perfect cylinder, a structure so strong and so tiny that millions could fit within the width of a single human hair. Weaving these infinitesimal threads into macroscopic cables kilometers long is a manufacturing puzzle we have only begun to solve. It requires us to move from creating grams of material in controlled conditions to producing it by the ton with perfect atomic precision in the noisy, challenging environment of space. This material revolution cannot happen in isolation. It must be accompanied by equally profound advances in how we build things. We would need autonomous robotic systems capable of working with this hyper-advanced material, assembling components with microscopic accuracy while floating in the vacuum. These would not be the robots of an automotive assembly line. They would need to be self-repairing, adaptable, and intelligent enough to manage the complex, unpredictable task of constructing a planet-sized object without constant human oversight. All of this relentless activity, from molecular fabrication to massive assembly, demands a source of power that dwarfs our current global energy production. The factories alone would consume more electricity than some small nations. This reveals a crucial truth about the orbital ring. It is not a single project waiting for one eureka moment. It is a grand technological symphony, a portfolio of interdependent breakthroughs that must all mature in concert. The development path for the ring is therefore a roadmap for a significant portion of advanced technology itself. The pursuit of each required component, from perfect nanomaterials to autonomous orbital factories, would generate world-changing spin-off technologies. The quest for the ring would inevitably give us stronger materials for everything from bridges to medical implants, more capable artificial intelligence, and revolutionary new methods of clean energy generation. This makes the entire endeavor valuable, even if the finished ring remains a vision for a distant century. The ambition forces progress across a dozen critical fields, proving that the journey toward such a monumental goal may be as important as the destination. This immense technological challenge is perfectly mirrored by our political and organizational limitations, suggesting that the greatest obstacle may not be the physics, but ourselves. The greatest hurdle for an orbital ring lies not in the void of space, but in the complexities of the human world. Constructing such a structure would be the single largest cooperative project in human history, demanding a political and social unity we have never before achieved. No single nation, regardless of its wealth or technological prowess, could possibly shoulder the financial burden or claim the authority to build something that encircles the entire globe. This project would require a global consortium, a permanent alliance of nations governed by a newly formed international space agency with unprecedented authority over its construction, operation, and security. We have a small-scale model for this in the International Space Station, a partnership of multiple countries that has maintained a continuous human presence in orbit for decades. Yet the scale of an orbital ring is so vastly different that it represents not just a larger project, but a completely different category of human endeavor. The issues of funding would be staggering, requiring nations to commit trillions of dollars over multiple generations, a level of long-term financial planning that challenges our political cycles. How would resources be allocated fairly? Would every nation contribute? And if so, would every nation have equal access to the ring's benefits? The legal jurisdiction is equally complex. The ring would perpetually orbit above every country, a moving piece of sovereign territory that belongs to all and none simultaneously. This demands a new legal framework for space, one that transcends terrestrial borders and establishes clear rules for commerce, habitation, and conflict resolution. Achieving this requires a depth of trust and a commitment to a shared future that humanity has rarely demonstrated outside of times of global crisis. Overcoming these human challenges may ultimately prove more difficult than solving the engineering problems, presenting a profound test of our collective maturity. This sobering reality forces us to confront the immense risks involved in creating something so permanent and so vital to our future. The very permanence of an orbital ring makes its potential failure a matter of global consequence. A catastrophic structural break would not mean a simple collapse. Instead, large sections of the ring moving at orbital velocity would begin a fiery and uncontrolled descent into the atmosphere. The energy released as these immense fragments burned and broke apart would be equivalent to countless nuclear detonations, scattering debris across continents and potentially triggering a temporary but devastating shift in the planet's climate. This is the ultimate engineering nightmare, a scenario where a single point of failure could lead to worldwide hardship. To prevent this, the entire philosophy of the ring's design must be one of graceful degradation. The structure cannot be a single, monolithic loop. It must be a network of interconnected segments, where the failure of one section is automatically isolated by emergency systems that seal the breach and redistribute the immense forces to the remaining healthy parts of the ring. Redundancy is the core principle here. Critical load-bearing elements would have multiple, independent pathways to carry the strain. If one cable snaps, its load is instantly transferred to several others, preventing a cascading unraveling. The magnetic systems that hold the cities would be designed to fail safely, meaning a power loss would not mean a sudden release, but a controlled, magnetic braking action that gently brings a city to a relative stop against the ring, allowing for emergency evacuation. Speaking of evacuation, the protocols would need to be as sophisticated as the ring itself. Each moving city would function as its own lifeboat, equipped with independent propulsion and life support capable of sustaining its population for an extended period. In a crisis, these habitats could detach and maneuver to safe orbits or designated space stations, while massive shuttle fleets from Earth would be on constant standby for a planetary-scale rescue operation. The financial and human cost of even a minor incident would be staggering, which is why safety cannot be an added feature. It must be the foundational design criterion, woven into every bolt, every line of code, and every operational procedure from the very first sketch. Grappling with these sobering possibilities is not a reason to abandon the vision, but a necessary step in making a truly informed choice about our future. It forces us to confront a profound ethical question, one that weighs the incredible benefits against the unprecedented responsibility of building something with the power to both nurture and endanger our entire world. Beyond the blueprints and equations lies a more profound challenge. We must ask if we should build this ring at all. This is not a question of engineering, but of ethics, forcing us to weigh our ambition against our responsibility. Does our species have a right to permanently reshape the space around our world, to add a human-made band to the sky visible for generations? This act would fundamentally alter the near-Earth environment, a domain that has belonged to no one and everyone since the dawn of time. Our obligation extends to those who remain below. A structure of such immense cost could create a stark divide, a celestial frontier accessible only to a privileged few, potentially leaving the majority of humanity on a planet stripped of its brightest minds and most ambitious capital. Would this become the ultimate expression of inequality, a glittering ring of prosperity floating above a world of struggle? And with such concentrated power and infrastructure, the potential for control is immense. The entity that governs the ring could command the flow of energy, commerce, and access to the solar system itself, raising the specter of a new kind of geopolitical dominance. The risks are not merely social. We are contemplating the creation of a fragile, planet-spanning system that would demand vigilant protection for centuries. A single act of conflict or a catastrophic failure, while remote, carries an existential weight that our civilization has never before had to bear. These dilemmas cannot be solved in a laboratory. They demand a global conversation, the development of a new ethical framework for space that prioritizes shared benefit and collective stewardship. The choices we make now, as the first foundations of our spacefaring future are being laid by current projects, will echo for millennia, defining the character of our civilization among the stars. The journey to an orbital ring is already underway in laboratories and launch facilities around the world. While the final megastructure remains a vision for the future, its foundational technologies are being forged today through a series of critical, incremental advances. The single most important hurdle is the sheer cost of reaching orbit, a barrier that projects like SpaceX's Starship are aggressively tackling. By developing a fully reusable launch system, the goal is to transform access to space from a multi-million-dollar endeavor into something more akin to a routine airline flight, slashing costs to a fraction of their current level. This is not just an improvement in efficiency, it is the essential economic key that unlocks every subsequent phase, making the logistics of moving millions of tons of material from the moon or asteroids a financially plausible endeavor instead of a fantastical one. Alongside this revolution in launch, we are learning the delicate art of building in the void. The meticulous unfolding of the James Webb Space Telescope's sun shield and mirrors was a masterclass in remote, autonomous assembly, demonstrating that we can construct incredibly complex and fragile structures far from Earth. This expertise is now being expanded upon with research into robotic 3D printing in microgravity, where future factories could fabricate massive components without the constraints of gravity, using raw materials harvested from space itself. Beneath all of this grand engineering lies a quieter, molecular revolution. In labs globally, scientists are making painstaking progress with carbon nanotubes and graphene, materials that promise the legendary strength needed for the ring's structure. We are learning to grow these materials longer and purer, moving from microscopic threads toward the macroscopic cables that could one day girdle a planet. No single team is working on an orbital ring today. Instead, thousands of researchers and engineers are solving disconnected pieces of the puzzle, assembling a toolkit whose ultimate purpose they may never see. Tracking the convergence of these fields allows us to peer into a possible future. The timeline for such a project is not measured in years, but in generations, likely spanning the better part of a century or more from initial commitment to final completion. This vast horizon invites us to consider the world that would undertake such a task, a civilization defined by its long-term vision and its collective will to build a new layer of reality around our ancient home. Such a project unfolds not in years but in lifetimes, a slow crescendo of human effort spanning more than a century. The first 20 years are a quiet revolution happening in laboratories, dedicated to solving two foundational puzzles. The relentless drive to slash launch costs must finally succeed, turning rockets into a truly economical railway to orbit. Simultaneously, in clean rooms around the world, material scientists are learning to weave the fabric of the future, moving carbon nanotubes from microscopic curiosities into strong, macroscopic ribbons. This phase is all about building the toolbox, creating the economic and material means to even begin. The following 3 decades would see that toolbox put to work on a humble but profound scale. We would not build a ring, but a single, sturdy link. A small-scale demonstrator, perhaps only a few kilometers long, would be assembled in low Earth orbit. This prototype would have no cities, no grand purpose other than to prove the core technologies. It would test the active support systems, validate the repair bot swarms, and demonstrate that a structure can maintain its precise balance against the subtle tugs of gravity and atmospheric drag. Success here provides the crucial confidence to proceed. The second half of our current century could then witness the true dawn of the megastructure era. With a prototype validated, the painstaking assembly of the first full-scale section would begin, a colossal arc stretching thousands of kilometers. This is no longer a test, it is the foundational backbone, the first permanent piece of celestial infrastructure to which everything else will one day connect. The completion of the full ring and the inauguration of the first moving cities, however, is a milestone for the 22nd century, a project for our grandchildren's grandchildren. This generational timeline is not a delay, it is a profound shift in perspective. It asks us to invest in a future we will never see, to lay foundations for a world we will never inhabit. Our role transforms from builders of the final product to planters of a cosmic seed. We are the generation that must make the choice, that must fund the first labs and launch the first demonstrators, trusting that future generations will carry the vision forward. This act of intergenerational faith may be the most challenging and beautiful part of the entire endeavor, connecting our present moment to a distant, starry future. The ultimate legacy of an orbital ring may not be the metal and carbon it's made from, but the new story it forces us to tell about ourselves. Building a structure that encircles an entire planet is an act that transcends engineering. It is a declaration, a physical statement that humanity has graduated from a species that adapts to its environment to one that intentionally engineers its surroundings on a planetary scale. We would no longer be merely inhabitants of Earth, living within the ecosystems we were given. We become architects of a new layer of reality, adding a ring of our own design to the celestial mechanics that have governed our sky since time began. This act fundamentally rewrites our identity. The very concept of home stretches beyond the soil of a single world to encompass habitats we have conceived, built, and set into motion with our own hands. We transition from being Earth-bound creatures to becoming citizens of a wider solar system, our sense of belonging tied to the entire neighborhood of planets and moons now within our practical reach. This expanded consciousness is perhaps the most profound product of pursuing such a grand vision. The ring becomes more than a tool. It becomes a mirror, reflecting back a version of humanity that is more capable, more united, and more responsible than we have ever had to be before. It challenges us to grow into the role its very existence demands, a thought that brings our entire exploration full circle, back to the simple, stunning idea of a city moving through the heavens. The ring in the sky is ultimately a question posed to our civilization. It asks us to weigh our deepest technological ambitions against the very structure of our societies and our place in the cosmos. This is not merely an engineering blueprint, it is a profound lens focusing our attention on the immense challenges of global cooperation, the ethical weight of planetary-scale construction, and the distant horizon of our cosmic destiny. From the elegant physics of centrifugal force to the intricate web of international treaties required for its governance, this single concept pushes us to think on a grander scale and to plan for a future that stretches across generations. The obstacles are undeniably immense, spanning material science, energy production, and political will. Yet the potential reward is a future unbound by a single world, a civilization with the freedom to grow and explore among the stars. This journey, one that may unfold over centuries, does not begin with a rocket launch or a robotic welder. It begins in the quiet space of our collective imagination. What kind of future do we wish to build for those who will come long after us? Share your perspective on this incredible possibility in the comments, and subscribe to continue exploring the frontiers of